Alright, so suppose p of x is a polynomial of degree d, which is greater than 0. We're going to take a look at c. So just read that to yourself and then kind of sketch out everything that you know and then try and write out what it is you're trying to show. And then go ahead and press play and we'll go from there. Alright, so the first thing that you're going to note, right, is that when you plug in this real number r, you get 0. We don't know what r is. It could be any real number, which is important because that means that we're not just testing for 1 or 0, right? In a and b, we said, okay, let's be very specific. Our root is at 0. We know root of 0. So then what do we know about the factor, or what do we know about p of x being divisible by x? Similarly, in part b, we said, okay, well, we know that 1 is a root. Here we're being totally unambiguous, or totally ambiguous. We're just saying, hey, r can be anything, but we know that r is a root. So if r is any root, we want to show that p of x is evenly divisible by q of x. So it's important to just remember, okay, we know that r is a root. If we plug it in to our polynomial, we're going to get a value of 0. And we want to show that p of x is evenly divisible by x minus r. So it's important to also think about, what does it mean to be evenly divisible? How would I show that 10 is evenly divisible by 2? Well, I'd say that 10 is 2 times 5 plus a remainder of 0. It's evenly divisible. If it weren't evenly divisible, that would mean I'd have to add some remainder. So if I can show that the remainder is 0, then I have proven that it's evenly divisible. So let's take this and apply it here. We want to show that p of x is evenly divisible by x minus r. Note that x minus r is just that factor that we're used to seeing when we have a root of any number, right? Maybe it's x minus 2. We have a root at 2. So what I'm going to show is that p of x is evenly divisible by this factor x minus r, right? That if I were to divide p of x by x minus r, I'd get no remainder. And so how do I show that? Well, I show that I can multiply p of x, x minus r times some other something, and when I add my remainder, we'll call it s here, that remainder is going to be 0. So think about what we have, right? P of x is similar to 10 in this case. And we want to show that x minus r, which is similar to 2, we want to show that 10 is evenly divisible by 2. We want to show that p of x is evenly divisible by this factor here. And so to show that, we have to say, hey, when we can find something that we can multiply x minus r by, and then there will be no remainder left over. So it's important to also think about, what is this other polynomial over here? Well, this is degree d, right? And this has a degree of 1. So what is the degree of this missing polynomial have to be, so that when I multiply it by a degree 1 polynomial, it'll be degree d. Think about, maybe an example in this case. If this were degree 3 and this were degree 1, you'd have to multiply it by degree 2. It's just going to be 1 less, because we're going to be adding a degree of 1 when we multiply by x minus r. So this will be a polynomial, some polynomial of degree d minus 1. Okay? In fact, we're just going to call that q of x. So we have that p of x is equal to x minus r times some other polynomial, we'll call it q of x, plus s. And we want to show, I'm missing a parentheses there, we want to show, look, this s here, it's got to be 0. There's no reason that I'd have to add on anything. This is evenly divisible, or it goes in evenly to p of x. So in order to do that, we might think, oh, well, we actually have to divide p of x by x minus r. Then you could do that, and you would be able to prove it. But there's a much easier route, and that is by checking what happens when you actually plug in r. So let's do that now. P of r, well, that would mean that I have r minus r, that I have this polynomial q of x. I plugged in r to it, so it's whatever I get when I plug in r, plus s. And at this point, we haven't figured out what this is, so how am I going to know what q of r is? Well, the good thing is it doesn't matter. Go ahead and pause right now and see if you can work this out and figure out why this doesn't matter, and then go ahead and press play again. So on the left-hand side, P of r, well, that's 0. And on the right side, well, what's r minus r? That's 0. So does it matter what Q of r is? It doesn't at all. Q of r is some number, right? Maybe it's 1,000,000, maybe it's 2, maybe it's 0.1. We don't care. And the reason we don't care is simply this. I have 0 is equivalent to 0 times anything is 0 plus s. So 0 equals 0 plus s. That means that my missing value here, s must equal 0. Okay, that's what I've come away with. So I've shown that, hey, if I have some root r, I know that it's evenly divisible by the factor x minus r. And we can just see that, right? The reason it's evenly divisible is because no matter what this polynomial is, this factor is always going to be equal to 0 when I plug in r. And so when I plug in r, it all just magically works out because this factor is 0. So kind of to just summarize what we've proven, which is something that's very valuable in mathematics, is that if you're given any polynomial and you're given a root, so let's just take an example. Let's say you're given some polynomial, we'll call it p star of x, and you're told that some number, we'll call it y, is a root, right? Well, then we know that p star of x is, I'll just say, evenly divisible by x minus y. And that's very, very helpful because now, let's say that you were trying to divide p of x by x minus y. Well, you know that it's evenly divisible, so that's helpful in checking your work. You know there's no remainder. And it also works very, very nicely to help us prove something that's very, very important, and that's part D. So if you're feeling ambitious, go ahead and try proving part D at this point. And if not, I encourage you to just really make sure you understand part C and all the steps that we took in order to determine that p of x was evenly divisible by x minus r.